Okay, so we have technically finished all the instructions for the 6502 emulator, and you'll notice this time I'm not on that previous website I was on that was had all the instructions on. This time I found this GitHub page by this Klaus2m5 who has written some tests for the 6502 processors, specifically really for emulators, or if you're making a FPGA simulator or something like that. So hopefully we can download this, compile it, get it loaded into our emulator and see how far we can get with it, and see if we can find any problems with the emulation that we've got right now, because it might be that we've done something wrong. We might have forgotten an instruction. It could be that there's undocumented behavior that is, that every 6502 ever did. So hopefully this program can tell us about what's going on with that, and hopefully we can get through it. It comes with its own assembler here. It does say it down here. This basically tests all valid opcodes and addressing modes. It has test for interrupt system and NMI, which is non-maskable interrupt, which we don't have on this version, but we don't have a way of injecting an interrupt into our processor at the moment. So that is something that is missing from it, even though we have technically implemented all the instructions. For it to be fully working, you need a way of interrupting the processor, which would be a pin on the processor in real life, but we don't have that. So we would need that if we wanted something. There is a decimal test. We haven't implemented decimal mode yet. Information about how to assemble it is in each source file, and he's saying the assembler is included here in the zip file. He won't convert to another one, which is fine, because he's given us the one that's there. And I think it's this one, functional test. So this giant program, it tells us how to compile it here with the compiler that he's already got. I've already had a go at this before, and one of the things I'm not going to do is write this Intel hex file. I'll just not do that because it doesn't load into our emulator very easily. And we can turn off the decimal mode testing in here, disable decimal. Yeah, so we can fully disable the testing for decimal mode at the moment because we haven't implemented it. But yeah, this program just runs through and just basically, wow, look at all that. So it just runs through and tries to find problems with your implementation. And I believe what actually happens is it says it somewhere in here. It does word it a bit weirdly, but because I've actually had a go at this previously, I kind of know how it works. It says loop on program counter determines error or successful completion of the test. And I was like, well, wait a minute. So if it succeeds or fails, it just loops. But the answer is that basically what happens is it goes through a part of the program, and if it finds a problem, it will just stick where it is. So it will just looping on the program counter just means it just loops back to where it is right now. So it just doesn't move. And from that, you can just stop your program, have a look at what it's doing, and then you can trace back the assembly code and then try and find out what went wrong previous to that. It will stick at the end. So this isn't a test we can leave in unit testing because it will never finish. But it is something we can use to find problems that we can write unit tests for that then we can fix. So we'll see how far we get through this. I know I did try this a while back before the emulator was finished, and it didn't get through all the tests. It stopped. It got through a few at the start, but it didn't get through them all. So we need to see how many of those we can find and fix. So I'm going to download this, and then I'm going to attempt to compile this. So the program we're interested in is this one. It's just a one file, and this is how we compile it. Oh, I need to extract. Yeah, so it recommends we assemble it like this, and I'm going to do all that, except I know not to do this Intel hex mode because I just want a binary file I can load. This Intel hex mode I don't know what it is, it's weird. Yeah, so this is our assembler, AS65. I've never heard of it, don't know what it is. We want all these. Just wants a file. Oh, you put your options in and you put your file that you want to compile in. So let's go back one into here, put these in, and the name of the file is this one. Okay, and we want to get rid of this Intel hex mode, which is S2. I'm getting rid of that. Oh, try to click in there with the mouse, can't do that. Right, I think that's it. There we go. That actually compiled something. Believe it or not, it was that quick. So what did we get? It gave us this. So this LST file, don't know what this is. This is, yeah, so this is like the symbols file basically that you get when you compile a program. This tells me which part of the program maps to which source program. So we'll need this to debug what's actually going on when it goes wrong, hopefully. And at the end of it, it writes this thing, which is, it basically wrote as a binary file. It doesn't write a file that's got like the amount of bytes it wrote at the header. It just writes the file straight out. So I just need to load this file in, and load it in at this memory address, and it's actually going to wipe out the whole of a memory address from A right through to the end. And then we run the program from there. So what's the file that it actually wrote? Is just 6502 functional test.bin. There it is, functional test.bin, 65,526 bytes. So let's put in some, I'm going to put in a unit test that I can't keep, but I'm going to put in a unit test that can load this file in and then try and run it. So I think we did something like that in a previous load program test. There we go. So let's copy that. So it's load the 6502 test program. I can't use this load program because I don't think, because it's not in a format that this actually accepts. This one reads the address, then gives me back. Yeah, it starts with the 2 bytes that are the address where to put it, and then it loads it in. This program's not in that format. So just going to write something in line here, I think. We know the start address is 400. And let's just do an open. Let's do this. So I just need to put the file path in there, which is this. It's quite a long file path. I'm just going to paste it right in. Like I said, I'm not planning on keeping this, so that's a long path. I wish I'd have picked a smaller path now. Right, so that should load it in, and then we can just, so can I just read the whole thing in like this? We know for a fact this is this many bytes. Element size 1, element count. And maybe actually, can I read it directly into the memory at the address we want? Maybe that's the better way of doing it. So this is going to go in at here. So it expects to be living here. And we want the address of that. And yeah. I think that's, let's just see if that works. Well, it compiled. Load, does that actually load anything into memory? So we're looking for stuff appearing around about here. Oh, it does. I think it does have some zeros at the start, this actually. 8001. I think that's loaded our program in. Yeah, it definitely got a file pointer. That is it. And for this bit here, we're going to execute forever because this thing just loops forever. So this isn't a test that can finish, and like I said, we can't actually finish this. So that's just some pretty crappy code to get this to put this into memory, but I think it's going to work. So let's just see if we get to here and execute something, because we're starting at this place. Basically, we're doing what it's telling us to do. Let's just see if we run. Do we get stuck? Right, so yeah, looks like that's running and it's stuck and it's not printing out any errors or anything like that. I hope that's correct. We could just pause it and have a look what it's doing. And it is fetching a byte. Oh. Yeah, it is going round. Let's just see what it did. Yeah, so it looks like, yeah, its program count is 675. Let's just see if we're stuck in there. Yeah, we are stuck in a loop at 675. So as expected, maybe this program, it's failed whatever this test is we tried to run in here. So in fact, that's the bit we saw. We saw 675 there. It was doing something. So let's see. This like list program or whatever it is basically the symbols file. So we can find out what's supposed to be happening there. What it was testing and why did it not progress, because I think that's error that didn't get to the end of the program. I think there's more than that. So here at 6, 7, where are we? So it was doing a compare. Basically, I think, because I've looked at this before, basically it's pushing the process status on the stack and then pulling it off to load it into the accumulator, and then it's comparing it to see that it should be 0 except break, pushed by software and reserved. Expected flags and always on bits. So this is the bit where we can look at the, it's probably easy to look at the actual file. Yeah, and I've looked at this before and this really confused me, but this says bits always on after PHP and break. So PHP is, let's have a look. This is where maybe this website is telling us how the 6502 works, but it's not telling us how an actual real 6502 works, which is, this says pushes a copy of the status flags onto the stack, which it does, and it doesn't affect any of these registers. So none of those in the actual processor are changed. So that's probably true, which is fine, but this is saying break and remember there's a bit in the processor status that actually isn't used. But this is saying that after push processor status, that the break command and the unused flag are always on the one you pushed onto the stack. I think that's what it's getting at. That's my best guess at that. That's what this FAO, I don't know what FAO is supposed to be standing for there. I believe that when you push to the stack, the processor status always sets some bits on the stack. Now I think I can find, yeah, and I think that's this page on this NES dev wiki. I found this when I was looking for, and it's not really mentioned anywhere else as far as I can tell, because the NES had the 6502 in it. The B flag, well, there are only 6 flags in the processor within CPU. When transferred onto the stack, there are 2 additional bits. These do not represent a register. Oh, what? These do not represent a register that can hold a value. The two interrupts, IIQ and MRI, and 2 instructions, PHP and break, push the flags onto the stack. In the byte push, bit 5 is always set to 1. So bit 5, I believe, is the unused flag, and 4 is set to 1, and 4 is the, what is bit 4? So 0, 1, 2, 3, is that right? 0, 1, 2, 3, 4. So the break flag and the unused flag are always set to 1 when either you do a push processor status or break. And of course this one also sets, side effects after pushing. That might be the documented part, but this is not documented. Bit 5 is always set to 1 and bit 4 is set to 1 from an instruction, or 0 if an interrupt line. So when you interrupt you don't set them, but when you break or you push processor status you do set them. Okay, so that seems to be quite undocumented, but this test program appears to be testing this. So 2 instructions, so this is the opposite. So the 2 instructions that pull the back from the stack ignore bits 5 and 4. So they don't pull those back off the stack. The only way for an interrupt request handler to distinguish IQ from break is to read the flags from the stack and test bit 4. So this is clearly some undocumented side effect that's not documented on here. This just says we push the process status onto the stack. This one's saying actually you push the process status on the stack and then set bits 4 and 5 to 1, and you also do it if you're doing break, which we didn't do, so that'll probably fail as well. So let's assume that this is true, for now because I've got a 6502 actually, but I'd have to get some programs on it to actually test this. Let's write a test for that. So let's find where do we put our PHP tests? Stack operations, is it? This is it, yeah, I think it's in here. PHP. PHP can push the processor status onto the stack. Now, actually, this test shouldn't change because if this is right, it's saying that you change them when they're on the stack, but when you pull them off, you ignore them. So that test is actually perfectly valid, I think, that whatever we expected before is what we expect afterwards. But we need another test that can actually look at the value on the stack and examine these bits and make sure that they are set. I think maybe we can just put that into this test. So basically, when we push onto the stack, we subtract 1. This 1 is going back up to the... So this is the address of the processor status on the stack. So let's just put that in there. Yeah, so that's the part of the test that's wrong. Maybe I'll leave this test the way it was for now, and we'll duplicate it and do a different one. So it's PHP always sets bits 4 and 5 on the stack. There we go. So what we want to do this time is let's push 0 in for the processor status. This is the address. That's the address of the processor status on the stack. Now this you would expect really that it's going to be 0. Don't need to test these other things on this one. Let's just check that that's... I'm going to take my test program out for now. Just get rid of this because this doesn't finish. So we're going to put this back in when we know it can work. So in theory that still passes right now, but we're going to make that fail, I think. Yeah, okay, that passed. So now we need to make this fail because what we actually want is... can we do flags? Status flags. Yeah. So what we want is we expect what was the bits 4 and 5, so it's the unused bit. Now that's weird. And break, is that bit 4? 0, 1, 2, 3. Let's just actually, instead of just writing status flag down, let's just write, let's actually write in what these are. 0 flag, and this interrupt, disable, is bit 0, that's 0, whoops, bit 1, bit 2, interrupt disable, bit 3 is decimal mode, and bit 4 is break, and 5 unused, unused, 6 is overflow, and 7 is negative. There we go. It's a little bit nicer, isn't it? So bit 4 is the B and the unused flag. Oops, we need the... Can we test that like that? Not sure if that's going to compile. Nope. I think we can just cast that to a byte. Can we not? You can't convert from that to byte. Why not? You are a byte. Have I got a... That's clearly you can convert. Okay. Please convert this to a byte. Please. I know this is a byte. Convert it. You won't do that either. Ah, you won't do that. That's not very helpful. Well, this is where this union has really made a mess of things for me again. Why can't you even reinterpret cast it? Because it requires a constructor. Conversion requires a constructor or user-defined conversion operator. Jeez. Okay, so that's the same. The reinterpret cast and this were the same, weren't they? All right, let's do it the way. Let's do it this way. C++ has failed me. And it's bits 0, 1, 2, 3, 4, and 5. Okay. Oh, whoops, let's OR it. Oh, we can just set it to that, actually. That's exactly what we want. There you go. So let's put a little note in here. Maybe I'll put a note about this, because this is some weird behavior. There's a lot of text here, a lot more than I thought. I've got a really big font because I do this on video, and normally this would be more readable, but I'm making it readable. Okay, that's a big comment, but this is the test that we're doing here, and this should fail this test. Let me just see, I've got these bits right. 0, 1, 2, 3, 4, 5. Okay, those bits are being set. And there we go. So they don't get set. So we can go and implement that now for PHP, and break's got the same problem. So let's just fix one at a time. I mean, that might allow our program to progress a bit further. So I'm going to get the same problem when I come to write these, I think. Oh, and of course it says it ignores them on the way back. That'll probably come out though as that one of our other tests should fail when I fix this one. So at the moment we're testing PHP always sets bits 4 and 5 in the stack. That is failing. So we fixed that. So now we can copy the processor status. So let's do this. And we'll actually do the maybe we could do it like this. I just want to make this more clear of what's actually going on here. So we'll use one, which is the break flag, and one which is the unused flag. So all that thing with the unused is the 5th one, and that is the 4th one. 0, 1, 2, 3, whoops, 4, 0, 1, 2, 3, 4, 5. And we're going to push that onto the stack instead of the actual. I think. Okay, let's see what we get. So we hopefully. Oh yeah. So what we did was we fixed that one, but we broke another one because now we're pushing in some bits and we want to ignore them on the way back. So that's probably good that we've actually got a test for that. So I'm going to move these out of here for now. We've got some bit masks up here somewhere, haven't we? Yeah, we actually have. No, we're saying putting bit on the end. Let's do that. Bit. Let's do that. Right, there we go. That's just a little bit of refactoring, but we still got PHP can push the processor status onto the stack. Is that the right one? Yeah, so that test now fails. This one here. And actually, I think it shouldn't, because when it reads it back, it just shouldn't. It should ignore those bits. So we just set all the other bits except that one. When the two instructions, PLP and RTA, pull back from stack and set all the flags, they ignore bits 5 and 4. Okay, so that's really what we've got to fix now. Let's ignore bits 5 and 4 when we PLP. And that was the test that's failing, was it? Oh no, because PHP is push. Actually, yeah, this test doesn't work anymore. Yeah, it has to actually test these values as well. So let's do the, let's just change this one out for the, does that fit on that line? Yeah, it does. Let's change that out there just so we're a bit more explicit again. What have I missed here? Nothing. Yeah, so that kind of has to be integrated into this test because we are looking at the value on the stack. And really, it ends up being this thing again, where we have to OR it with all this stuff. So we've had to kind of fix that test as well. So those bits are always set on the stack, even if they weren't set before. Yeah, now that fixes that part of the test, but break does it as well. We haven't fixed that, and it has to ignore them when it reads it back, when PLP reads it back. So we need a test in PLP. PLP can pull a value from the stack into the processor status. So in this case, we just put this random value in. And maybe we can do the thing where we're going to OR this with the flags again. It's the break bit. So when it comes back out, these bits shouldn't be set. Let's just see what that does. So we should still get 42 out of the other end. What value are we actually gonna? What value are we gonna write? Yeah, so we didn't write 42, and that's what I really wanted to know. So this is like getting more complicated now because we're actually doing some debugging. But let's just see if we do 42. Okay, so that doesn't have bits. That doesn't have bits 4 and 5 set, so that's okay. That's what we want. That is actually a good number to test with. That we load this back in, but we're not. We should expect 42 back in there. We shouldn't expect these two bits to appear. So that does fail. So we can go in and change that now. PLP. So we pop the byte from the stack, but this time we're not going to pop it straight into there. So we pop that from the stack, and we are going to have to mask out the unused bit and the break flag bit. Wait a second, this isn't finished yet. So we actually want to pump that into the processor status, but we want to make sure that these bits are ignored. So the best way to do that would be to zero those out and then AND this. What would be the easiest way to do that? Because if they were set before, we want to leave them the way they were. So we just want to ignore what's in there, really. So let's bitwise invert that. This is where this is going to start looking weird. Bitwise invert that, and that will just give me, that will give me zeros wherever those bits are. And then I can AND that with that, I think. And that is going to turn those bits off on the value I read from the stack. So basically I'm ignoring them. I think then I have to zero this and then AND this. Whoops. Is that the easiest way to do that? That doesn't seem particularly clever way of doing that. Let's just see if what I've got there works, just before I try and tidy that up. I don't even know if what I'm doing there is actually working. And it's not. It is not working. Now there's my 72. That's giving me my 42 back, but I don't want to just blat that 42 in. I want to make sure that oh, idiot, because you're supposed to be ORing it. Okay. That does pass. Oh, okay, so I almost had that right. So that just reads it back in, but ignores these 2 bits. But it's not quite right because it might be actually removing, this might actually be removing bits if they were set. So let's write another test for that. And what I mean by that is, if I had a value here, this one, let's just see what that might be. If I had a value that was just those 2 bits set, so it might be something like this, doesn't need to beat anything else. The value that I expect on the stack is just those 2 bits set, but when I read it back, it should still just be those 2 bits set because we don't change them. So we ignore the ones that were on the stack, but we leave those as they are. So I expect this to fail. Yeah, so PHP ignores bits 4 and 5 when pulling from the stack. So yeah, we've wiped out that data basically, which is what I shouldn't have done. So let's go in and fix that one now. I think I want to, instead of setting it to 0, I want to AND it with, is this right? If I AND it with that, it just masks everything off except those 2 bits, and then I OR back in the value that doesn't have those 2 bits back in. So that's what I want. Now let's past it. So that is a lot more confusing than the way it was before, but that's what we've got right now. I think that fixes PHP and PLP. It doesn't fix break and RTI, but I wonder if we get a bit further through our program now. But at least we know that's a problem. So I'm going to put my program back in and see if that did anything for us. I mean, it's still going to stick. Yeah. So it sticks, and then we stop it and see where we are. Now we're still stuck somewhere. But we're stuck in a totally different place. So that's a good sign. That means it progressed a bit further. So we did something that this program liked, which is all good. So let's just see what's at that place. 37CA, we got quite far. We got a lot further. Wow, we did all this. Wow. Oh my word. Unless it jumped around to a place that was nearly finished. 37CA. Oh, wait a minute. I didn't even turn decimal mode on this, so is this going to fail on that? 37CA. Oh, yes, this is more always on bits. Oh, this is the... So what was it doing here? Yeah, this is the break. Test break on stack. Is that right? Is this what it's doing? Break and IRQ. Okay, yeah. So that's good. That means that's the other part of this that we haven't done yet. And it looks like that's the bit that's not working. So that's good news. Now, that looks like we passed a load of tests as well in between there and the break test. I didn't actually disable decimal in this. I mean, and that decimal should throw an exception in ours if it doesn't work. So maybe it hasn't got to decimal yet, I don't know. Maybe they're afterwards. So let's do the same thing we just did for the break command. And we actually just did break in the previous video. So this is the same thing. Break can push the program counter and status onto the stack. In this case, yeah, we're going to expect that the processor status on the stack has these bits set, the unused bit and the break flag. So that's the bit that's changed. It's just that test, I think, actually. When RTI, that also has to ignore those bits as well when it comes back. So this might create a couple of weird tests here when we fix one of these. There we go. So let me just check that again. So yeah, it's saying that it's wrong, but actually it's not, because we expect these to be set when we actually do the break command. So let's just see. So this push PC onto stack. This is where maybe we need, yeah, because we're pushing byte onto the stack there. So this is the bit where we should probably factor this part out and make this into, yeah, this needs to be its own function now, I think, to do the so we'd have to keep writing the same thing over and over again. Because now this is more complicated. Push PC onto stack. Takes those. Doesn't take any functions, doesn't return anything. Is that everything? Takes the memory as well. So, right, break flag. We can swap this out in here. That's all we want in that bit. And we've done a little bit of refactoring. Probably might have to refactor that in a minute, but we're not doing that yet. And then down here in break, oh, we already had, oh, push process. Oh, I called it PC again, idiot. Right, okay, let's go back. Processor status onto the stack. Oh my word, what am I doing? And I said program counter, processor status. Jesus, what am I doing? There we go. Push PS onto the stack. Push PS onto the stack. Push PS onto stack. Call that onto and push PS. We'll call that 2 because we've done it the same way on that one as well. Let's rename that. Oh, hello. Push PS to stack. Okay. Are we fixed? Nope. Because RTI can return from an interrupt. Right. So RTI isn't working correctly now because the value we pushed on in break is just getting popped back off. Now that's the bit that we need to refactor from the other one. Let's just look for it in here. There it is. Let's refactor that out as well, because that got more complicated quickly. Pop PS from stack, ignoring bits 4 and 5. Ignoring bits 4 and 5 on the stack. Okay, this bit got replaced with all that. Okay. And we're still back where we were because I haven't fixed the other one yet. That gets replaced with that. And I think... oh, it didn't work. RTM leaving the CPU and leaving the CPU in the state when it entered. Let's have a look. Let's put that back the way it was then for now. Why doesn't that work? Because the processor status should be back in the state when it entered, I think. Oh yeah, it looks like have we got those bits? Oh yeah, those 2 bits came back out. Okay, that's fine, because that's the bit of code that we don't want. We want to pop processor status from the stack. So why isn't that fixing it? We got 10. What? Which is just bit 5. That's really odd. What the hell happened there? We got bits 4 and 5 back off of the stack, and then we should have masked them off, which we got 0. And then the processor status somehow has ended up with the unused bit set. Is that right? Have I got this wrong? Because RTI actually isn't. These all get set from the stack, but it ignores the. This one's saying it ignores the break command. This is saying here. 2 instructions, PHP, pull back from the stack, set all the flags. They ignore bits 4 and 5. So this is saying this doesn't set this from the stack. So this is conflicting information. I don't know which one of these is right. Can they both be right? Which one of you is correct now? Now we've got a discrepancy. This is also saying that the interrupt flag is changing as well. What? Well, there you go. Conflicting information. What do I do about that? I mean, if you had a real 6502, you could test this, but they can't both be right. They can't be being set from the stack and be getting ignored. It can't be both. Doesn't seem right that it would ignore the break flag after return from interrupt when it might have been the interrupt that actually set the break flag. I wonder if they mean by ignore bits 4 and 5 is that they mean that bits 4 and 5 get set to 0, and that's different to it being ignored. That's actually being zeroed. This claims that RTI clears bit 4, which is break, of the status register popped off the stack by RTI. The documentation doesn't indicate that happens, but it might. So again, this is a different explanation of what you're saying. I don't actually know. As far as I understand it, RTI and PHP don't clear bit 4. That is, they don't write it back to the stack. They just ignore it. So then, if you come back from a break with an RTI, then no one ever clears break. So is that correct? That doesn't seem right. The break command is set when break instruction has been executed and an interrupt has been generated to process it. So that would imply that you came back from the break and it's not set because you ignored it. That can't be true. That seems like crap. I don't think that's right. I am confused. There's too much confusing documentation. It'd be nice to have a 6502 to actually test this on. But this seems like it doesn't make any sense to me. But maybe, am I just reading this wrong or something? But these 2 pages can't both be true. And you can't ignore that. Let's test the program that we've got with this the way it is right now. Let's see what we get. Because that unit test fails, but what does this do? Because in theory, this does what this page says, but it seems like utter nonsense to me. So it is pausing there. And we are at 37CF. Which doesn't seem like we even got as far as we did before. Is it the same? Should have added an interrupt disable. I think that's where we're stuck. So there's actually some other problem here. So it was expecting, this is again, it's pulled the value off the stack, and it was expecting those 2 bits to be set, which is what we wanted. But it also expects interrupt disable to be on as well. And what's M8? Ah, that was on this page as well, though, wasn't it? Interrupt disable is set to 1 on the stack value. So apparently what was wrong was this, I was misreading this page. This is one of the things that's wrong anyway, is that this side effect after pushing is that the interrupt flag is set to 1, not the interrupt flag that was pushed onto the stack set to 1, which is what I did here. So that is wrong, which is weird because it doesn't say that that's the case on here. This is saying break command is being set to 1, but it's not saying the interrupt disable is being set to 1. But apparently it is, but after this has been pushed. So does it actually say this here anywhere? The break instruction forces the generator to interrupt the current stack. Yeah, it doesn't say that. So maybe this documentation is missing this part here, that this is set to 1 after it's been pushed. This is also set to 1. But it doesn't matter because it always writes this 1 to the disk anyway at this point, or to the stack. Because if I set the interrupt to 1, it actually starts working here. This is set I'm going to call it set interrupt disable flag after. Oh, that's a horrible thing now, isn't it? So what's going to happen here is the flag interrupt disable gets set after we've pushed it onto the stack. And I can put this here to make it a bit more clear. Okay. I think that's right. So push PS onto stack. So this one is set interrupt disable after, which is false, and push PS. This one is true. I mean, and in theory, we could just push that, we could do that there, but it looks like maybe we've got to do that in other places. I'll leave it like this for now. And let's see if we can get a bit further. And the answer is, so we're still stuck in that program, but we are at 3.5b1, which is a little bit further. We got a little bit further. Are we around here somewhere? Yeah, we passed that test anyway. So we're still in the break test, but we passed it, but we got a little bit further, but we didn't progress much further. 3.5b1. What is this one all about? I have no idea. Break return 0. What is that? Address of break return. Oh, it's comparing the high and low bits of the return address. Proper return on the stack. Ooh, looks like I might have messed that up as well. So let's take this out for now. And let's see where we're up to with the actual other tests. We're getting a bit further, but maybe we're doing something. Again, this comes down to the fact that we may have a working emulator, but not working in the way the actual 6502 behaved. So I've still got this thing of like, I've got 2 failing tests now. So what can we tidy these up? Break will push PC and PS onto the stack. Let's have a look. This one. So that's wrong now. We don't do that. What we do is we expect the interrupt disable to be true after that, because that's what it says. I don't know if that's really true, but that's progressing through our test. Maybe we should put a note on this one as well. Okay. And then we just back to this, the fact that we don't know what the hell is going on here in the fact when it says they're ignored. I don't believe that's true. So that's unsolved at the moment. So I'm going to stop this here for now, and we're going to come back to this later. I'm going to try and figure out exactly what in the hell this is talking about, because again, we have got some differences now between what this is said, where interrupts getting set to 1, and this one is saying that it's not being affected. So this might be that there was a difference in certain 6502s. This might be an error in this documentation, but clearly this test program is expecting that interrupt to be set, and I don't know what the hell I'm supposed to do with this other one, because we've got this discrepancy, haven't we? The processor status is coming back differently, because I think I've actually made this so that this doesn't change the processor status. It's just the fact that this break flag is still on because we said we ignored it, and I just don't think that that can be true. But I mean, we've passed all the break tests so far, so I'm going to leave that the way it is for now, and then we have to put a note on here. Says that says that B flag is set from stack, but it says that B and unused flag are ignored when setting from stack. They cannot both be true. Huh? So what the hell is that about? What is all that about? 2 instructions, PLP are pulled back from stack, they ignore bits 4 and 5. And I will quote that there. So this would be so much easier with an actual 6502 that we could just write a little program and we could really find out what it does here. But in the least, we've got a little bit further. It may be that this program that we've got has actually got some other problems. Maybe we're pushing the wrong, maybe it expects the return address to be something else, I don't know. But I feel like we've got something a bit better now, because we've definitely progressed quite a way through that test program, but not all the way through. I mean, we've got a clear, how far have we got? I mean, this is, yeah, we've got through 14,000 lines of this, assuming that it is running from top to bottom like it kind of claims, that we've actually got through a lot of this stuff. But yeah, actually nearly got through the whole thing. Cool. So it looks like there'll be another video then where I'll try and decipher all this junk and find out who's true here, who's giving us the right information. Are you setting this from the stack, or are you ignoring the stack? It's like, which one is it? So the documentation's wrong. So have to have a look at that in the next video.